So our last topic is trigonometry, and it's not in our textbook. So we're going to use the notes and then the photocopied assignment pages or the assignment pages on the Moodle site to complete the last topic of Math 49. So many of you probably remember trigonometry from some point in your past. We are going to do trigonometry with right angle triangles. So we're going to use Pythagorean theorem and the SOHCAHTOA stuff. If those things jog your memory at all, that's the sort of stuff that we're going to be doing in this chapter on trigonometry. So like I said, not in the textbook. There is an assignment. You should hand it in. It says not needed to be handed in, but you should hand it in. There is a drop box for that on the Moodle site. And trigonometry is really useful, and it's probably the most useful bit of the math that we've been doing. You will notice that there is no practice test for the trigonometry just because we're up against the final, and it just gets a little bit too tight in timing, I think. So newsflash that triangles have 3 sides and 3 angles. It's true about all triangles. That's what triangles are. And the cool thing about the angles in a triangle is if you took any triangle, and you could do this, you could cut any triangle out of a piece of paper. And if you were to take the corners and rip the corners off, and in a better world, I'd be able to manipulate these things and take these corners and line them up. What you would find is that these corners, whoops, I was going to switch to the blue again. These corners, if you were line them up, take this one and put it there, and take this one, you have to kind of flip it on its head and put it there, and take this one and put it there, you make what is a straight line, because a straight line is 180 degrees. So the point of this, and it's much better if we could actually do this in class, is that all of the angles in a triangle, the sum of the angles in any triangle, always add up to 180 degrees. And that's really a useful piece of information as we start talking about triangles. So we're going to start off talking about about angles with this fact that they add up to 180. Then we're going to talk about sides with Pythagorean theorem, and then we'll do the linking of sides and angles with the SOHCAHTOA stuff. I'll keep talking about that as we go. So like I said, we only are going to deal with right angle triangles in this course. And so if a triangle is a right angle triangle, that means that one of the angles is a 90-degree angle in it. So that means the other 2 angles would add up to 90 degrees, because these 2 together would be that 180 that I tried to establish with my goofy little drawing over here. So in these ones, if we were to determine the missing angle, you could take 180 and minus 30 and minus 90 to figure it out. Or because it has a right angle in it, and like I keep saying, all of our triangles will, we could take 90 minus 30 to figure out this missing angle as being 60 degrees. And so that's all we're doing with these ones is figuring that out. And so the missing angle would always be 90 minus whatever the angle you know is. And so that one would make this 11 degrees. On the last one, this one's going to be a 50 degrees. And to show my work on that, it's 90 minus 40 to get to that 50 degrees. So starting off easy, not a big deal. The sides in a right angle triangle are the next parts of the note. So before we get into the Pythagorean theorem, we're going to start with a little bit of kind of convention in math and in geometry, and we're going to use this as we move into trigonometry. So in these ones, the sides in a right angle triangle, the side opposite to the 90 degrees, so opposite to means across from, is always the hypotenuse. If you remember that word, you know, it might be something that you remember about triangles. The other 2 sides are called legs, and the legs are perpendicular to each other because they have that 90-degree in between them. So what I'm talking about here is that this would be the hypotenuse, and these 2 would be the legs, right? So in these ones, there's also a bit of information that we could talk about as far as standard, whoops, I was trying to erase that, about standard ways of dealing with triangles. So we've got the hypotenuse and the legs, but we also have a way of labeling these with letters because, you know, how we love letters in math. So we could label this triangle as A, B, C. The capital letters, so the uppercase letters, are the angles. And so that's what I just did with that red purple color there, right? I labeled this triangle as triangle ABC. Now, if I wanted to label the sides of this, the sides get matching letters, but this time lowercase letters, and it's across from. And so across from A would be side A. Across from C would be side C, and across from B would be side B. So that convention of angles getting the uppercase letters and sides getting the lowercase letters, and that corresponding, that idea of going across from the angles to give the letter of that corresponding side. And again, in these ones, oftentimes C is the hypotenuse, but technically you could label up a triangle with any letters you wanted. So C is often the hypotenuse, but the hypotenuse is always the side that is across from this right angle corner. So we're going to practice some of this. So this one says, label the triangles and indicate which side is the hypotenuse. And so in these ones, remembering that angles get the uppercase and sides get the lowercase, I could label the sides. Again, I'm going across from the letter to get to the corresponding side. And on these ones, I would label the angles using the uppercase letters for the angles. And again, that's that corresponding, it's across from those lowercase letters. Again, you can see here, it doesn't matter what the letters are, it still has this same convention. On these ones, I'm going to take yellow and I'm going to circle the hypotenuse. So this would be the hypotenuse, and this would be the hypotenuse, and that would be the hypotenuse. The hypotenuse is always across from that 90-degree angle. So as we get into the sides, remember we started with all angles and the sum of the angles was 180. Now we're getting into sides, and that's where we get into the Pythagorean theorem. This is the Pythagorean theorem. And what we do with the Pythagorean theorem, we use it to solve for an unknown side when two of the sides are known in a very specific kind of triangle, a right angle triangle. And this is really, again, something that you've probably seen. This is the classic example where C we identify as the hypotenuse, and this is the hypotenuse squared. The hypotenuse squared is equal to the sum of the square of the other two sides. And this picture of that is really meant to kind of illustrate that, because you can see here that if we took side A and squared it, so that would be 4 squared, which would be 16, and side B squared, which is 3, squared is 9, and added those together, that should equal the length of C squared. Now this triangle is a 3, 4, 5 triangle, and a right angle triangle at that, and it's the classic one that fits this Pythagorean theorem. But the point is that all right angle triangles fit this model. So if you squared this, it would always be the sum of the squares of the other two sides. And that's what we do. Solving for the unknown sides uses algebra, and we've learned, tricks for this. So to solve for the unknown, you have to rearrange the squared variable. You have to take the square root of both sides. So again, with these, sometimes people remember it, but sometimes they don't. So I'm going to make sure that I show all of my work. So in this one, using what we've just talked about, so a squared plus b squared equaling whoops, that's not a c squared. And the c squared, this is the hypotenuse. So here, if we were to identify the hypotenuse in A, it's that side x. And so fitting it into this formula, I would have that a squared, which I'll call 3 squared, plus the other leg squared should equal x squared. So if I keep going on this, and I could use my calculator, or I could show my work on some of these. It is 25, but I haven't solved for x. I have solved for x squared. That's what this is talking about up here. You have to take the square root of both sides. So we talked about this in chapter 9 with the radicals. If I square both sides, the square root of x squared is x. And in this case, the square root of 25 is 5. That is a perfect square, which is awesome. It is the example that we just saw at the top, but oftentimes we have to approximate these. So when you're solving for a side, we're going to go to 1 decimal place. So round sides to 1 decimal place. And that's a fairly arbitrary decision. I've just told you to do that. We don't really have rules for operating that way. That's just going to be our guideline. We're going to round our sides to the nearest tenth of a unit. So in this one, again, it's key to identify the hypotenuse. And if I were to fit this triangle B into my Pythagorean theorem, I would have 3 squared plus x squared equaling 7 squared. I have to reorganize this. You can leave these as squared numbers, or you could actually evaluate them if you wanted. So I'd have 9 plus x squared equaling 49. Solving for x, I'd subtract 9 from both sides. I'd get that x squared equals 40, but then I have to do this wacky bit. To solve for x, I have to take the square root of both sides. Because we're dealing with geometry, that we're again with the principal square root, in this one I have to use my calculator because it's not a nice, neat, perfect square. And we're going to round this to 1 decimal place. So that missing side in this case is 6.3. I'm going to talk through 2 more and then I will put the answers up for the last ones. Again, with these, oftentimes people do have some memory of this. I think the key point is finding the hypotenuse and then fitting it into that equation that is the Pythagorean theorem. With these ones, you can use your calculator. I generally do this with my calculator, and I can do it all in one step. So I could take 6.5 squared plus 6.5 squared, and then take the square root of it. And I don't need to write all that down on the page because it gets ugly and messy. So my answer here is 9.2. Again, I'm doing all of this in my calculator. Again, down here, I'll show the setup of it, but again, I generally use my calculator. So again, find your hypotenuse, the sum of the squares of the other 2 sides equals the square of that hypotenuse. You could rearrange these. You might have that x squared equals 13.2 squared minus 11.5 squared. And then you could do that on your calculator. You're going to have to remember to take the square root of both sides so that you can actually say what x equals. And again, I don't generally show all of my work on this. Sometimes I will say that x equals 13.2 squared minus 11.5 squared because that shows what my thinking is at least, but I rely on my calculator to do that work for me. So my answer would be 6.5 in this one. The other ones I'll set up, but I'll stop talking. The last one has some tricky rounding on it, but that's the answer that I get. So that is the first 2 bits of this part 1. So we've gone through the angles in a triangle, and now we've done a little review on Pythagorean theorem. So hopefully you're feeling pretty good on that. I'm going to finish up this video with an introduction to the trigonometric ratios. So these are the trig ratios. We know them probably from the memory device. So, ka, tawa. So if that's something that you remember, or you're like, I vaguely remember that, that's what we're going to talk about on this page. So getting into that, the trigonometric ratios are sine, cos, and tan. They are the buttons on your calculator, and they're built up on the ratio of sides two angles. And so basically we're going to start off here with those sides. So we know that all right angles have a hypotenuse and they have those two legs. So the legs have differing names depending on the angle that is our reference angle. So we could talk about the leg that is opposite to the angle we care about, or the leg that is adjacent to the angle that we care about. It's these O's and H's and, oh, sorry, that's an A, and H's that are in this memory device here. So we had the three ratios, the sine, the cos, and the tan, and there is a relationship between these lengths of the sides of a triangle. So the hypotenuse is the longest side. I lost my cursor here. Hang on. Oh, there it is. Longest side. And we know we've done this before. It is always across from the right angle in the triangle. The other two sides are labeled depending on their location to the known angle or the angle that is being solved for. So sometimes I call that the reference angle. It depends on your point of view. So the opposite means across from, because we've already been doing that with the sides being opposite to the angle letter, right? And adjacent, if someone to sit adjacent to you it means that they sit beside you. And so again, it depends on the angle. So we're going to practice labeling these triangles. So label the hypotenuse, which is probably easy. We want to label the opposite and the adjacent. And in all of these, we're going to use A as our reference angle. So again, those legs of the triangle have names that change based on which angle is your perspective. I've seen people that draw like a little smiley face down here. So it's as if you are down at this angle A, and that helps us label these. So in this first example here, it's always easiest to label the hypotenuse. And so the hypotenuse would be here, and I would just label it as HYP. If I were to label the other two sides, the one that is across from my reference angle where I am would be opposite. And the side that is beside my reference angle would be adjacent. So all of these are going to get labeled that way. It is always easiest to label the hypotenuse. And then take a look at that reference angle. That's the one that tells you the opposite and the adjacent. I'll pause for a minute on the last one there, give that one a shot. And I would label the last one just like that. It's pretty easy to get these backwards. You do have to kind of keep your wits about you. It's not difficult, but somehow, we make common mistakes. So the three basic ratios are ratios of the lengths of the side of any right angle. And that's where we're getting these names in relation to the ratios that we're talking about. These ratios have a decimal value that is the same regardless of the size of the triangle. So you can basically scale a triangle up and it makes the same angle. So they relate directly to the size of the angle making that triangle. On our calculators, we can use the sine, cos, or tan button to tell us what that decimal equivalent is. And this is a super powerful tool that's built into your calculators. Back in the day, you used to have trig tables. They would tell you those, but those values are programmed into your calculator. So this is where we remember our memory device. So the sine of an angle, theta, is how you say that Greek letter. It is the basic symbol that is any angle. So that's what goes in there. So the sine of an angle is equal to the opposite over the hypotenuse. We remember that as so, if you will, in that memory device, right? Sine of an angle is opposite over hypotenuse. The cosine would be the, ka, I can't say that without sounding silly. So it's the cosine of an angle is equal to the adjacent over the hypotenuse. That's the ka bit of ka toa. Toa is meaning that the tangent of an angle is equal to the opposite over the adjacent. And what we're talking about here, this opposite over adjacent bit, is the ratio of the sides of the lengths of a triangle. And so this is how we use this memory device. It sounds silly when you say it, but that's what we're doing. And again, that symbol there is theta, and it represents your target angle. Okay, so to prove this concept with yourself, this is not the best exercise. I pulled it from the old resource that we used to use. I'm going to change it slightly for use this time. Basically, what we're supposed to be doing with the next page is proving to ourselves that this actually works. So I'm going to flip past the instructions there. You get the benefit of the video and me showing you what we're going to do. If we were to imagine using a ruler, which I can't use on this, and measuring these sides, I'm writing down the numbers that I get as the length of my sides here. And so I've measured really, really carefully. You're going to have to take my word for it. And so in these ones, if I were to put these into the chart here, if I were to use this as my reference angle in all of them, that makes this side opposite, right, on all of them, and this side adjacent because it is beside my reference angle, or my target angle, sometimes I call it. Okay, so we're going to fill in the sides, or fill in the information. So this is triangle 1, this is triangle 2, and triangle 3. The chart has already filled in triangle 1, so we're going to fill in the chart for triangle 2. Triangle 2's opposite side is 3.85 centimeters. The adjacent side is 5.50 centimeters. If I were to take the ratio of opposite over adjacent, that would be 3.85 over 5.50. And if I were to evaluate that in my calculator, so that's how we're going from here to there, I end up with 0.7. This is the ratio of those two sides, right? So for the third one, if I were to fill in the blanks here, the opposite side is 5.88. The adjacent side is 8.40. If I took opposite and divided it by adjacent, and using my calculator for this, I get a decimal equivalent of 0.7. You can see here that this angle on all of them is the same. So that means that there is a fixed ratio between the lengths of the sides that are involved in these triangles. And that is defined by this decimal equivalent that stays the same. So just for fun, we're going to practice using our calculators a little bit here. Take your calculator and punch in tan 35. You want your calculator to say DEG. If your calculator tells you you are rad, then we need to switch the functions on your calculator. So punch in your calculator tan 35, and what you should get is 0.7. What this is illustrating is that consistency, right? If we have this fixed angle here, there is a fixed ratio between the sides of the triangle making that triangle, or making that angle. So more with these ones, using your calculator. In these ones, all of our calculators do work a little differently. So if you have difficulties with your calculator, please let me know. In these ones, we want to solve, actually, let's try these ones down here. So no, we'll do this first. So in these ones, we're solving for an angle. If you want to solve for an angle, you have to use second function sign or the inverse sign. And so you use the inverse or second function button on your calculator. So in these ones, we're going to practice just using your calculator on these ones, and then we'll pick up with this next day. So sine theta would equal 0.5, right? That's the ratio between those. So on your calculator, punch in second function sine 0.5, and you should get a 30-degree measurement. Just practice using your calculator on this one. On these ones, you could take 2 divided by 4, and then in your calculator, hit second function sine, and just see if you can get that theta, or the angle, would equal 30 degrees. Again, we're solving for an angle here, and this is the less straightforward way where you have to, use that second function button. One more, and if you've noticed, we're just scaling these up. There should be that same decimal equivalent and that same value being made. If you were to guess on this one, it's going to be a 30-degree measurement. But again, practice using your calculator. If you didn't try punching in 16 divided by 32, then try it on this one. All of our calculators do work a little differently. What we're supposed to be finding is that it's 30 degrees. And again, if you were to simplify that, it would be a 0.5 decimal equivalent. And so your calculators can go between the decimal equivalent and that angle. That's the information that's programmed into them. Here's some more that are a little more random, but also, again, just having you check using your calculator. When we're solving for the angle, so here it's not theta representing the angle, but a d representing the angle, this is the decimal equivalent. So anytime we're solving for an angle, you have to use that second function button. I'm sure we have some calculator issues. This one does say round to the nearest degree, so I'm putting the answers up rounding to the nearest degree. And again, this is really just a bit of a dry run for us to see if we can practice using our calculators. The last part of the notes is the easier with your calculator. So these ones mean that it's a little bit more straightforward to do. So in these ones, most of our calculators will just be punch in sine 50. And this is going to give you the decimal equivalent. We're going to go to 4 decimal places and round as needed. So again, with these ones, not a lot of a trick, really just calculator work. I'm going to throw the answers up and make sure that your calculator is working for you. So that's the end of the first video. At this point, you can do the assignment, numbers 1 through 7.